Hey everyone. So we've just gotten through our implicit differentiation, which is one of the hardest bits we've done this year. And to be honest, we're going to level up. So the next topic is called related rates, which makes some logical sense. Like if I am blowing up a balloon at a constant rate for the volume, the rate that the radius is changing is going to change at a rate that's not the same as what the volume is doing, but it's related to it, hence the name related rates. So there's a lot of things like this. And, like if I have a circle, I change the radius of it, of course the area changes. So does the circumference. There's a lot of different problems like this. And if you search on YouTube for, related rates calculus, you will see that there are approximately 11 million videos that have been made. And quite honestly, there's a lot of really good ones. And I really encourage you to look at more of them. They have a little more technology than I have on some of them, so they can actually animate the stuff that they're doing, which can really be helpful. Sadly, my video skills are still not there. So let's just take a look at this. So these 5 steps you see in the box, you should write these down. Like hit pause, write them down. So, although right now they probably don't make any sense yet, but that's okay. We're going to go through them. So here's our situation. A sphere is inflating at a constant rate of 3 cubic centimeters per second. How fast is the radius increasing when the radius is 1 centimeter and also at 4 centimeters? Just a little note. When you see centimeters cubed per second like that, or, squared or whatever, you say cubic centimeters. You don't say centimeters cubed. You just sound kind of weird. So just putting that out there. Okay, so first thing we want to do, and in this case, like drawing a sphere is like kind of like, like, hey, look, sure, it's a sphere. It has a radius r. So in this case, it's kind of like the step 1 didn't work very well, to be honest. But this is a decent problem to start with in terms of, like, relatively speaking, it is simpler than a lot of the other ones. Okay. The next is the know, want, and when step, as I like to call it. Like we're going to list out, like, what are the things we know? What is it that we want? And when do we want it? Because this is going to really help us out in a moment. So we can look at all this stuff here. And we know that the sphere is inflating at a constant rate of 3 cubic centimeters per second. Oh, so we know what the rate of change is for the volume. So in the things that we know, we can say that dV dt, the rate of change of volume with respect to time, is 3 cubic centimeters per second. I like to include the units in here too. And then what is it that we want? Well, the thing we want, how fast is the radius changing? And so and on these steps, we're going to end up doing a lot of translating from English to math. Like, how fast is the radius increasing? So the thing we want is actually translating this to calculus terms. We want dr dt. And then when do we want it? Now. Oh, wait, that's probably other things that we want. For the when, we want it when r is 1 and also when r is 4. Once in a while, you'll have like multiple things. So obviously, like if you're increasing at a constant rate for your volume, at 1 centimeter for your radius, the radius is going to be increasing a lot faster than when the radius is bigger. Because if you have a really big sphere and you add 3 cubic centimeters per second, your radius is hardly going to change at all. So it's kind of good to pay attention to these kinds of things to just see if you're making any sense. Okay, so we listed the know, want, and when. That's our step 2. Step 3, write an equation relating the variables, usually a common formula. Our textbook likes to put things out there like, recall that, and then they give you a formula you don't recall at all. It's nice of them to pretend that we recall the things, though. So I'm going to say, recall that. Let's see. Is there something that relates the radius and the volume? We have to recall this, maybe Google it, maybe it's given to us. You just don't know. And when we're writing the equation, this isn't a calculus thing at all. Like, ignore your step 2 in a way. You could switch 2 and 3 if you wanted those steps. So can we write some formula that relates the volume of a sphere with the radius of a sphere? Well, yeah, that is volume is 4/3 pi r cubed. No, I'm not assuming you remember that formula or know that formula, and that's okay. Okay, now when we were doing implicit differentiation, we had all these x's and y's mixed up. We're going to end up with like v's and r's, and the weird part is the invisible t that's in here. We're deriving with respect to time. So like the derivative of volume with respect to time is dv dt. The derivative of the radius with respect to time is dr dt. So, and as we're doing this deriving with respect to time, this is a chain rule thing. In fact, if it helps you, rewrite this as 4/3 pi, put the r in parentheses, cubed, because it helps us see it a little bit better. Okay, so derivative of v, dv dt. 4/3 pi, that's just a bunch of numbers multiplying it, making the rate of change that many times steeper, so I can just go like that and hit times. Okay, chain rule, derivative of the outside. I have 3, blah, 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 do for the exponent. Keep the inside the same, r. And then times derivative of the inside with our chain rule, so times dr dt. Quality control step here, looking at this equation, this derivative we've just written, like, is there a place to put the things we know, the dv dt? Yes. Is there the thing we want? Yes. So that's good to kind of check that and go, is the thing I want showing up? Because if it didn't show up, you messed up. Okay, solve for the desired rate. So I'm going to solve for dr dt because that's the thing that I want. All I need to do is divide by stuff. And actually, I can cancel those 3's out. So dv dt over 4 pi r squared is dr dt. So that's our step 4. Okay, step 5, this is the straightforward-ish bit, I suppose. Plug in numbers and then answer the question. When we answer the question, you have to be super careful about this. Just saying dr dt equals a number is not answering the question. You're trying to show you know what you're talking about. The way to do that is with a sentence with units. So we'll get to that in a second. So at r equals 1, I get dr dt is my dv dt. I can plug the 3 in. Could have done that a step earlier, actually. And then 4 pi r squared, so 4 pi times 1 squared. So I just have 3 over 4 pi. And the units on this would be, since r would be centimeters, t in seconds, this is centimeters per second. So answering this in words would be like, when r equals 1, the radius is increasing, and I'm going to suggest / recommend / really force this on you. Say words like increasing or decreasing and avoid the word changing, because changing is ambiguous because that could mean smaller or bigger. And as humans, we wouldn't say, like, if something was decreasing, you wouldn't say it's changing a negative amount. You would say it's decreasing an amount. So just throwing that out there. So it's increasing 3 over 4 pi centimeters per second. There's no need to get this 3 over 4 pi into a decimal. If you do put it into a decimal, be careful with that, because notice that I put that 4 pi, that denominator, into parentheses to get the 0.238. So be really careful there. By the way, that 3 over 64 pi, that's just me working ahead, because that is what happens with r. So at r equals 4, we can just do the same thing. So plugging in, we get 3 over 4 times pi times 4 squared. And actually, that's an okay answer too, and you would just write the sentence as well. When r equals 1, or sorry, when r equals 4, the radius is increasing 3 over 4 pi times 4 squared. You can leave it like that, believe it or not. Just as long as you throw some units on it and answer the question in words, because it's just clearly showing you know what you're talking about and that you found the thing you were intending to find. There is going to be a second video that I make with a second example, so stay tuned.